From fabrication to installation, massive pipeline systems power megaprojects, where precision engineering, logistics, and coordination transform raw materials into critical infrastructure worldwide. The PVC pipe extrusion line is a fully integrated industrial system designed to manufacture high-quality plastic pipes with precision, consistency, and high output. At the heart of the line is the BA 125/28D twin-screw extruder, powered by a 110 kilowatt motor, which provides strong plasticizing and stable material flow. Virgin PVC material is fed into the system through a dedicated dosing and loading unit, while recycled regrind material is added through a separate feeder, allowing efficient and environmentally responsible production. Inside the extruder, both materials are heated, mixed, and melted into a homogeneous PVC compound. The entire process is carefully monitored by a Siemens S7 industrial PC-based temperature control cabinet, which ensures precise thermal stability and smooth extrusion conditions. The molten PVC then passes through an extrusion head capable of producing pipes up to 500 millimeters in diameter, forming the basic cylindrical shape. After exiting the die, the hot pipe enters a two-stage calibration trough, which is 10 meters long and supports diameters up to 630 millimeters. Here, vacuum and water cooling stabilize the pipe's dimensions. This is followed by a 6-meter cooling trough that fully solidifies the pipe wall. Next, a pipe marking unit prints identification and production data. A 4-caterpillar haul-off system pulls the pipe smoothly through the line at a constant speed. The pipe is then cut to length by a planetary cutting unit with universal clamps, ensuring clean, accurate cuts. Finally, an inline belling unit forms solvent cement or O-ring sockets, completing a finished, ready-to-install PVC pipe. First, connect the hydraulic oil hoses to the machine carriage and then to the hydraulic power station. Next, connect the heater cable to the heater and the hydraulic power station, making sure both connectors lock firmly with an audible click. After plugging in the hydraulic power station, switch on the circuit breaker and verify operation by moving the machine carriage. Place the two HDPE pipes onto the carriage and secure them in the jaws. Tighten all jaws firmly with a ratchet so the pipes are held rigidly. At the same time, turn on the heater using the on/off button. Install the trimmer on the lower piston rod and place its stand on the upper piston rod, then release the blocking ball. Start the trimmer and close the carriage so the cutter faces both pipe ends. When continuous, even chips appear from both sides. Open the carriage, stop the trimmer, and remove it along with all plastic chips. Close the carriage again to check that both pipe ends are perfectly aligned. Then open the carriage to prepare for drag pressure testing. Turn the pressure relief valve counterclockwise to zero the pressure and reduce the regulated pressure to minimum. Push the direction lever to maximum and slowly turn the pressure regulated valve clockwise until the movable carriage starts moving. The pressure shown on the gauge is the drag pressure PT. Set the soaking time T2 and cooling time T5 on the timer. Close the carriage and increase pressure until the gauge displays P1 plus point. Once the heater reaches its set temperature, Confirm the actual surface temperature. Clean both pipe ends carefully to remove any dust or contamination. Insert the heater plate between the pipe ends and close the carriage to allow soaking. When the soaking time T2 ends, open the pressure relief valve, open the carriage, and quickly remove the heater. Immediately close the relief valve and push the direction lever to raise pressure to the welding pressure P5 plus point. Hold this pressure for about 10 seconds, then slowly release the lever. After the cooling time T5 is completed, release the pressure completely and remove the welded pipe joint from the machine. Before installation begins, every StormPro pipe is subjected to pre-inspection to ensure it is free from damage, deformation, or contamination. Pipes are stored on flat, firm ground that has been cleared of debris and combustible vegetation. They are laid horizontally on transverse bearers at least 75 millimeters wide and spaced at a maximum of 1.5 meters apart. For long-term storage, pipes may be nested, provided that sockets are fully supported so the ends remain free from loading. Different pipe sizes are stacked separately to prevent distortion. Trench preparation begins by forming the 4 installation zones: the bedding zone, side support zone, overlay zone, and trench fill zone. The trench is excavated as narrow as practical while meeting all health and safety requirements. A compatible granular material such as crushed rock or sand is placed on the trench floor to form the bedding layer. This layer is leveled to the required grade and compacted to provide continuous support for the pipe barrel. Shallow recesses are excavated where sockets will sit so that the pipe remains uniformly supported along its length. A laser level is used to ensure accurate fall and grade, and a compactor is used to achieve proper bedding density. Once the bedding zone is complete, pipe installation begins. StormPro pipes from DN150 to DN600 may be cut anywhere along their length and reused with the standard socket system. DN750 and DN900 pipes have a different spigot geometry, so if they are cut, a coupling must be used for jointing. All connections to pits, structures, and house leads are installed after bedding preparation and before side support backfilling. Jointing is performed using StormPro's rubber ring system. For DN150 to DN600 pipes, one rubber ring is stretched over the spigot and placed between the first and second corrugations from the spigot end. For DN750 and DN900 pipes, 2 rings are installed, one between the first and second corrugations and another between the second and third. The rings are checked for even seating around the full circumference. Vinidex jointing lubricant is applied to the inside of the socket, taking care not to allow lubricant under the rubber ring. The spigot is aligned straight with the socket and inserted carefully. Grit or debris is removed before jointing. A short stub of pipe without a rubber ring is placed against the socket to protect it while force is applied. The pipe is pushed until the spigot contacts the internal shoulder of the socket. Smaller pipes can be joined using a crowbar, while larger sizes may require winches, come-along devices, or a machine bucket, always with socket protection in place. The required jointing force increases with pipe diameter, and correct grade is maintained according to discharge velocity tables. StormPro pipes connect to pits and head walls by inserting the spigot end first into the structure, normally working upstream. Service connections are made using either programs or pro saddles. For programs, a hole is drilled in the valley between corrugations using the specified hole saw. The grommet is flattened and inserted so its locating wings sit correctly in the pipe profile. Lubricant is applied, then a PVC spigot and socket insert is fitted, followed by solvent-welded pipe. For pro saddles, a flange is placed over the drilled hole, the saddle is aligned, and hex screws are tightened through the preset holes before connecting the service pipe. After jointing and connections are completed, side support and haunching begin. Granular, free-flowing material is placed and compacted evenly around the underside and sides of the pipe. This interaction between pipe and soil provides the system's strength. Material is compacted in layers to maintain alignment, prevent distortion, and achieve uniform support. The overlay zone is built up to a minimum of 150 millimeters above the crown of the pipe, with compaction applied at the trench edges rather than directly on top of the pipe. Finally, the trench is backfilled to the finished surface using excavated material or specified pavement layers for trafficked areas, ensuring both construction and long-term loading requirements are satisfied. The installation process of ductile iron pipelines begins after a straight, properly graded trench has been prepared. Once the trench bottom is compacted and leveled, a bedding layer of fine soil or sand is spread to support the pipe evenly and prevent point loading. This foundation ensures that the heavy DI pipe will remain stable after placement. Using an excavator, workers lift a large black ductile iron pipe and carefully lower it into the trench. The machine operator positions the pipe slowly to avoid damaging the protective coating. Ground workers guide the pipe with slings and hand signals so that it is perfectly aligned with the previously installed section. The spigot end of the new pipe is oriented toward the socket end of the pipe already in place. Before jointing, a rubber gasket is inserted into the groove inside the socket. This rubber ring is cleaned and checked to make sure it is free from dust, sand, or deformation. Lubricant is then applied to the gasket and the spigot to reduce friction and allow smooth insertion. This step is critical for creating a tight, leak-proof seal. A hydraulic pushing device is then used to gently push the smooth spigot end of the pipe into the socket of the previous pipe. Workers monitor the alignment carefully, ensuring the pipe enters straight without tilting. Guide bars and supporting tools are used to prevent joint misalignment and to protect the rubber gasket from damage. As the pipe is pushed forward, it slides through the lubricated rubber ring until it reaches the correct insertion depth marked on the pipe's surface. This confirms that the joint has been fully seated and the seal properly formed. After connection, the joint area is inspected to verify that the gasket has not rolled or been displaced. Once the pipe is correctly positioned, initial backfilling is performed around the pipe with fine material to secure it in place. The bedding is compacted carefully along the sides of the pipe to lock it in position, while keeping the joint stress-free. The installation then continues with the next pipe section, forming a strong, durable, and watertight DI pipeline system. The installation process begins as each DN600 ductile iron pipe section is carefully lowered into the prepared trench using lifting slings and an excavator or crane. The pipe is guided so that its spigot end aligns precisely with the socket of the previously laid section. Workers place rubber pads and timber blocks beneath the pipe to avoid coating damage and to keep the axis perfectly straight. Once the pipe is positioned, the BLS anti-slip coupling is fitted around the joint. First, the sealing gasket is placed inside the coupling to ensure full water tightness. Then, the steel housing of the BLS joint is closed around the pipe ends and temporarily held in position. After that, the locking segments are inserted. These hardened segments bite into the outer surface of both pipe ends when tightened, creating a powerful mechanical grip. Bolts are then tightened in a cross pattern using calibrated torque wrenches. As the bolts are progressively tightened, the locking segments are pushed inward, anchoring the coupling firmly to the ductile iron pipes. This creates a continuous restrained pipeline in which axial forces are fully transferred through the BLS system. Because of this mechanical restraint, the thrust forces generated by high-pressure water inside the DN600PN50 pipeline are absorbed entirely by the anti-slip couplings. No concrete thrust blocks are required, even at bends, valves, or changes in direction. After each joint is secured, alignment and elevation are checked again before the next pipe is lowered. The process is repeated section by section, forming a strong, continuous, and pressure-resistant penstock line ready for final backfilling and commissioning. The installation process starts with the trench being excavated to the required depth and alignment, followed by careful leveling and compaction of the bedding. Once the trench is ready, a tractor or lifting machine lowers each 300 mm ductile iron pipe section into position using slings to avoid damaging the coating. Workers then clean the spigot and socket ends, ensuring that no dirt or grit can interfere with sealing. A rubber gasket is fitted into the socket groove and lubricated to allow smooth insertion. The spigot end of the next pipe is aligned precisely with the previously laid section and pushed into the socket using a hydraulic jack or mechanical puller. This action compresses the gasket to create a tight, watertight joint. After jointing, the pipe is checked for correct grade and alignment. Finally, the trench is partially backfilled and compacted around the pipe to stabilize it before the next section is installed. The installation process begins by carefully cleaning the spigot end of the HDPE double-wall corrugated pipe and the elastomeric rubber gasket. Any dust, sand, or debris is removed to ensure a perfect sealing surface. Next, the rubber ring is placed into the groove at the edge of the spigot and visually inspected to confirm it is evenly seated and free from twists or damage. After that, both the spigot and the rubber gasket are thoroughly lubricated to reduce friction during assembly. The bell, or socket, of the receiving pipe is then cleaned and lubricated in the same way, ensuring smooth insertion and preventing damage to the sealing ring. Once the joint surfaces are prepared, the pipe section is lifted using lifting equipment and carefully lowered into the trench. The pipe is positioned on the prepared bedding so that it is stable and properly supported. With the pipe in place, the spigot and bell are precisely aligned to avoid angular stress during joining. The end of the pipe is then prepared for insertion, often with assistance from a backhoe that provides controlled pushing force. Finally, the spigot is pushed into the bell until a tight, watertight spigot-to-bell joint is achieved, forming a secure and leak-proof drainage connection. Each 8-inch C900 pipe section is first lifted by a crane and carefully lowered into the trench that has already been excavated and leveled. The operator positions the pipe slowly so it aligns precisely with the previously installed section. Ground workers guide the pipe by hand and use slings to fine-tune its orientation, ensuring the spigot and bell ends are correctly lined up. Before joining, a worker thoroughly cleans the bell socket and the spigot end to remove soil, dust, and moisture. A water-based pipe lubricant is then applied evenly around the rubber gasket and the spigot. This lubricant reduces friction and allows the pipe to slide smoothly into place without damaging the sealing ring. Once lubricated, the crane gently pushes the new pipe section toward the existing pipeline. Crew members use pry bars and alignment tools to keep the pipe straight and prevent angular deflection. As the spigot enters the bell, steady pressure is applied until the reference mark on the pipe reaches the edge of the bell, confirming full and correct insertion. After the joint is completed, the crew checks the alignment and slope of the pipe to ensure it matches the design grade. Any minor adjustments are made by slightly lifting or repositioning the pipe before final placement. This procedure is repeated for each section, gradually extending the C900 pipeline along the trench. With every connection, the sealing surfaces are cleaned, lubricated, and carefully joined, creating a continuous, watertight 8-inch water main ready for pressure testing and backfilling. The process begins with the excavator carefully excavating a trench along the designed alignment of the drainage system. Using its tooth-digging bucket, the machine cuts into the ground layer by layer, removing soil, clay, and compacted material to reach the required depth. The operator constantly checks the trench width and depth, ensuring they match the engineering drawings and the slope needed for gravity drainage. A uniform trench bottom is essential, so the excavator trims and levels the base after the bulk material has been removed. As the digging continues, spoil material is placed to the side of the trench, keeping enough distance from the edge to prevent collapse. The trench walls are kept straight and stable so that the concrete pipes will sit correctly without being forced out of alignment. If the soil is loose or wet, the operator slows down and shapes the sides more carefully to reduce the risk of cave-ins. The excavator also forms a smooth, continuous gradient along the bottom of the trench. This gradient is critical because even a small deviation could later cause water to collect inside the pipe instead of flowing freely. By making small, controlled movements, the operator ensures the trench base is even, without high spots or soft areas. When the trench reaches its final profile, the excavator cleans out any loose soil or debris, leaving a firm and well-shaped foundation ready for the bedding material. This precise trench preparation is the foundation of the entire pipe-laying operation, ensuring that each concrete drain pipe will be properly supported and aligned once installed. After the trench is fully excavated, the excavator begins placing bedding material into the bottom of the trench. Using the same bucket, the operator lifts loads of fine aggregate or selected fill and carefully lowers them into the trench. Instead of dumping the material all at once, the bucket slowly tilts forward so the material flows down in a controlled stream. This prevents segregation and ensures the bedding spreads evenly across the base. The operator moves the bucket along the trench, distributing the material to create a continuous, uniform layer. This bedding acts as a cushion that supports the concrete pipes and helps distribute their weight evenly over the soil. By controlling the drop height and flow of material, the excavator avoids disturbing the trench bottom, maintaining the correct slope and level. Once the bedding is in place, the excavator is used to lift and position the concrete drain pipes. The machine attaches lifting chains or slings to the pipe, raising it carefully from the ground. The operator then swings the boom toward the trench, keeping the pipe steady and balanced. With precise control, the pipe is lowered slowly into the trench. The excavator holds it just above the bedding while workers check alignment and orientation. After confirmation, the operator gently sets the pipe onto the prepared base, ensuring it sits evenly and matches the direction of the pipeline. Before connecting the next pipe, workers apply sealant to both ends of the concrete pipes. This adhesive or rubber-based compound is spread evenly around the joint surfaces to ensure a watertight connection. Once the sealant is applied, the excavator pushes the new pipe toward the one already in place. The operator uses slow, controlled movements to bring the two pipe ends together. As the excavator applies steady force, the joint slides into position, compressing the sealant between the surfaces. Workers guide and check the alignment while the machine completes the final push, creating a tight, secure joint that prevents leaks and ensures long-term durability of the drainage system. The ruptured 18-inch cast iron main was first isolated by installing 3 line stoppers so water could be held back while work proceeded. A nearby hydrant and a leaking bypass valve were taken out of service and exposed. Crews then cut out the damaged section of pipe using a chainsaw fitted with a water spray to keep the thick iron cool during cutting. Once the heavy 1-ton pipe segment was lifted out, a new replacement section was lowered into the trench. High-max repair couplings and steel collars were carefully positioned to join the new pipe to the existing main, requiring precise alignment. Dozens of bolts were tightened, first with power tools and then by hand, to create a pressure-tight seal. After air was vented through a small copper line, pressure was equalized and the line stoppers were slowly opened, allowing water to flow through the repaired main again. The project begins with the removal of a 36-inch horizontal double-disc gate valve that has been in service since around 1946 on a steel water transmission main. The existing valve and its restrained collars, known as dog ears, must be carefully cut out to make room for the new valve, which weighs over 8,000 pounds. First, the 2 longitudinal weld seams on the steel pipe are ground smooth in the sealing areas where the high-max couplings will be installed. The bolts connecting the dog ears are then cut, while the collars themselves are left in place to restrain the new valve. After marking the cut lines, technicians check the outside diameter of the steel pipe using OD tape to confirm it falls within the coupling range. The welder then makes the cuts, and the old valve is lifted out of the pit. Before installation begins, workers recheck the opening to ensure there is enough space for the new valve and couplings. The exposed pipe ends are thoroughly cleaned, with scale removed and rough areas smoothed to create proper sealing surfaces. The new vertical gate valve is prepared above ground by installing ductile iron mechanical joint nipples on both ends. These nipples are locked in place using megalugs. The high-max couplings are measured and prepared. Because the steel pipe has a smaller outside diameter than the ductile iron nipples, the inner gaskets are removed from the side that will fit over the nipples. The centering pins are backed out, and the couplings are lowered into the pit and slid onto the steel main. The valve, with nipples attached, is then lowered into position and set on blocking. Lubricant is applied to the ductile iron nipples, and the high-max couplings are pushed back over the joints. The centering pins are tightened to ensure the correct gap for pipe deflection. Finally, the coupling bolts are tightened evenly from side to side, and a torque wrench is used to bring each nut to its specified value, completing a secure and fully restrained installation. The coupling process of a 14-inch polyductile pipe begins with careful preparation of both pipe ends. First, the two pipe sections are positioned on stable supports and aligned so that their center lines match precisely. Any dirt, moisture, or debris on the pipe ends is removed to ensure a clean contact surface. This is critical because even small contaminants can weaken the quality of the joint. Next, the internal coupling is inserted into one end of the first pipe. This internal sleeve is designed to fit tightly inside the polyductile pipe, providing mechanical alignment and structural continuity between the two sections. The second pipe is then moved into position and slowly pushed over the exposed part of the internal coupling until both pipe ends meet at the center of the joint. At this point, the internal coupling holds the two pipes perfectly aligned, preventing offset or angular misalignment during welding. Once the pipes are correctly joined, the welding stage begins. A welding machine or heat welding equipment is applied to the outer joint where the two pipe ends meet. Heat is evenly distributed around the circumference of the joint, melting the pipe material at the interface. As the molten material forms, controlled pressure is applied so that the softened plastic from both pipe ends flows together, creating a single continuous wall. After welding, the joint is allowed to cool naturally while remaining clamped in position. This cooling phase allows the material to solidify and fully bond around the internal coupling. When cooled, the welded area becomes as strong and leak-resistant as the original pipe, ensuring a reliable and durable 14-inch polyductile pipeline connection. When each pipe joint is ready, two heavy steel pipe ends are carefully aligned and brought together using internal clamps and side booms so their center lines and bevels match precisely. The alignment is critical because even a small offset could weaken the weld or cause defects later during automatic welding. Once the gap and roundness are verified, skilled welders begin the first operation: manual external root welding. Using shielded metal arc welding, the welders apply a continuous root bead around the full circumference of the joint. This initial weld fuses the two pipe edges together and seals the joint from the outside, preventing movement during the next stages. The welder works methodically, controlling arc length, electrode angle, and travel speed to ensure full penetration into the joint. The purpose of this manual weld is not to provide final strength, but to lock the pipes in perfect position and create a stable foundation for machine welding. Because the pipes are large in diameter and wall thickness, several welders may work around the pipe at the same time, moving in coordinated segments to complete the full circle evenly. Once the entire circumference is covered, the joint becomes rigid, allowing it to withstand the forces applied later by the automated welding system. After the manual weld is completed, surface preparation becomes the next critical step. A technician uses a high-speed angle grinder to remove excess weld metal, spatter, and surface irregularities from the temporary manual bead. This grinding operation smooths the joint so the automatic welding head can travel evenly along the pipe's surface. Any sharp edges, slag, or uneven buildup could interfere with the precise movement of the CRC welding equipment, so the grinder is guided carefully along the full circumference of the joint. The goal is not to remove the entire weld, but to create a uniform, clean profile that allows the automated torch to maintain a constant arc distance and stable heat input. The grinding also exposes fresh metal, eliminating surface contaminants that could lead to porosity or lack of fusion. Once the surface is visually inspected and confirmed to be smooth and continuous, the joint is ready for the high-precision automated welding stage. With the joint prepared, the CRC Evans P625 automatic welding system is installed around the pipe. The welding bug clamps onto the pipe and moves along a fixed track, carrying multiple welding torches that deposit filler metal with extreme accuracy. Unlike manual welding, the machine maintains a constant travel speed, wire feed rate, and voltage, producing highly consistent weld quality. The P625 performs several passes, including hot pass, fill passes, and cap pass, building up the weld layer by layer. Each torch follows the joint exactly, ensuring uniform penetration and bead shape around the entire circumference. Sensors and control systems adjust parameters in real time to compensate for any slight variations in pipe geometry. This automated process produces a dense, defect-free weld with high mechanical strength. Once the final cap pass is completed, the pipe joint becomes a continuous, pressure-rated section of pipeline, ready to move forward to inspection and coating.